Okay, good morning to all of you. So today we are going to see the how to calculate the I want to explain the theory behind behind finding the natural frequency of free vibrations of the spring mass system. Okay. So the aim of our experiment, okay, is to find the natural frequency of free vibrations of the spring mass system. Okay. So here, if you see this diagram, okay, if you observe the diagram, there is one fixed end, and to this fixed end one spring is attached, okay, and just when the spring is attached, we need to measure the unstretched length of the spring. Okay. So why we need to measure the unstretched length of the spring is that we have to calculate the theoretical natural frequency of free vibrations, as well as also we have to calculate the experimental natural frequency of these free vibrations, and we have to compare these two, that is theoretical as well as experimental natural frequency we have to compare. Okay. So that is why we need to measure this theoretical natural frequency. So in order to measure this theoretical natural frequency, so first we have to calculate the unstretched length of the spring, okay, so without attaching any mass. Okay. So but what is meant by free vibrations, first we have to understand that one. So free vibrations are the vibrations those are set up in a body when that body is given an initial displacement without any external forces acting on the body. So those are known as free vibrations. Okay. So now here, without attaching a mass, so what is the unstretched length of the spring? First we have to measure, and once we attach the mass to the spring, so what is the stretched length, and the difference between these two lengths, the unstretched length and the stretched length, will give you the static deflection of the spring mass system. Okay. So once we get the static deflection of the spring mass system, so substitute in this formula. So that is 1 by 2 pi root over L by G multiplied by root over G by delta L. Okay. Sorry, I mean to say the theoretical natural frequency is equal to 1 by 2 pi multiplied by root over G by delta L. So this delta L is nothing but the static deflection we are going to find out, okay, by means of this experimental demonstration also in the next session. Okay. So first we need to find this static deflection, substitute in this formula. So this G, small g is the acceleration due to gravity, and this n th is the theoretical natural frequency of the spring mass system. Okay. So first we need to understand how to calculate this unstretched length of the spring. Okay. And so already we have seen how to calculate the unstretched length of the spring now. Okay. So just attach the spring to the fixed end. Okay. So without any stretching or without any external forces is acting on the spring. Okay. So that we can note the unstretched length L1. Okay. And now we attach a mass to this spring, and we need to measure this L2, the stretched length, okay, after attaching the mass to this spring. Okay. So here in our experimental demonstration, so these springs, okay, whatever I have represented here in this diagram, these springs are the closed coil helical springs. Okay. So that we will see in the experimental demonstration. Okay. So once we calculate this theoretical natural frequency of these free vibrations, so by experiment we will demonstrate, okay, by experiment how to calculate the natural frequency, that is experimental natural frequency of free vibrations, and we will appreciate the fact that there is a correlation between the theoretical and experimental natural frequency of these free vibrations of this spring mass system. So then we can we can easily say that that the natural frequency of free vibrations what we are obtaining by theory as well as experiment are in mutual agreement with each other. Okay. So, in the next session we will see the demonstration of the experiment of this one, okay, and how the natural frequency can be calculated by experimental demonstration. Okay. So, thank you very much all of you. To all of you, today I am going to demonstrate the experiment related to finding the natural frequency of free vibrations of spring mass system. Okay. So, this is the just a basic setup. Okay. So, to this setup we add some spring and we need some mass, we attach some mass to the spring. Okay. So, and from that we need to find the natural frequency of this system, okay, of the spring mass system. Okay. So, here, so this is the spring attached to a fixed end of this fundamental setup. Okay. So, this is the closed coil helical spring. Okay. So, now we need to find the natural frequency of the free vibrations if a mass is attached to this spring. Okay. So, as you already know, so the natural frequency of free vibrations, so how to define free vibrations is that, so free vibrations is the oscillations, those are set up in a body. So, when given an initial displacement without the effect of external forces acting on the body, so those are known as free vibrations. Okay. Or natural vibrations, you can say sometimes natural vibrations also. Okay. So, for these free vibrations, so we need to find the natural frequency of the free vibrations of the spring mass system. Okay. So, that is our aim of this demonstration, experimental demonstration for us. Okay. So, now here we need to take the as we already seen in the previous session. Okay. So, how to calculate the stretched length and unstretched length. Okay. So, we need to calculate the unstretched length first of all. Okay. And after attaching the mass we need to see the, we need to measure the stretched length, and the difference between the two will give the change in length. Okay. Change in length with the addition of mass. Okay. So, here, so let us see, so what is the unstretched length of this? Let us measure this unstretched length of the spring by means of a measuring tape here. Okay. So, exactly 7.5 centimeters is the unstretched length of the spring. Okay. And coming to the, so now we attach some mass to this spring. Okay. Okay. So, this is the hanger that is attached, and to this hanger we add some mass. Okay. Another mass. Okay. So, now we have to take the mass of the hanger as well as the weight into consideration, another weight what we have added into consideration. So, here, so first we need to note the weight. So, that is 338 grams. Okay. So, the mass attached to this spring is 338 grams, and so in kgs it is 0.338 kgs. Okay. And now we need to measure the stretched length of the spring. Okay. So, what is the stretched length of the spring? Take measuring tape like this again. Okay. So, we need to measure the stretched length of the spring. Okay. So, almost it is 15.5 6 centimeters. Okay, the stretched length of the spring is 15.6 centimeters, and the corresponding mass already we noted, that is 0.338 kilograms. Okay, and we need to measure the static deflection. So that static deflection is nothing but the change of the stretched length and the difference between the stretched length and the unstretched length. Okay. So now for 20 oscillations, so what is the time taken? So we have to note the time taken for 20 oscillations. Okay, so that we can calculate the experimental natural frequency of this free vibrations of the spring mass system. Okay. So, so first the vibrations need to be set up in this system. Okay. So by giving an initial displacement to this mass attached to this spring, okay, so we get the vibration that will be set up. Okay. So here you can see, by giving an initial displacement like this, okay, the vibrations are set up in the spring. The free vibrations are set up in the spring. Okay. So here no damper is attached. Okay, and and no external force is acting. Okay. So these are free vibrations of this spring mass system. So now we need to take the time for 20 oscillations. So just take an instant of time, so that you can comfortably calculate the time taken for 20 oscillations. Okay. Okay, so it is 14 seconds, exactly 14 seconds, okay, for 20 oscillations that we got. So this is the first reading. Okay. So with corresponding mass of 0.338 kilograms. Okay. So now we add another mass to this existing mass, so that how the frequency, is there any change in the frequency, or if there is no change in the frequency, how it is going to occur. So that we are going to see by another by taking another reading. Okay. So now I add some mass to this spring mass system again, so that the stretched length will be different for this corresponding mass. Okay. So now the mass that is there, the total mass that is there, that is 0.438 kilograms. Okay. And the stretched length, now we have to measure the stretched length again by the measuring tape. So take the measuring tape again, slowly keep the measuring tape at the point you want to measure. Okay. So it is almost 19.3 centimeters. Okay. So it is 19.3 centimeters. So L2 for the corresponding mass of 0.438 kilograms is 19.3 centimeters. Okay. So now so we can calculate the corresponding static deflection, that is L2 minus L1 for this mass. Okay. And also now we need to take for 20 oscillations, what is the time taken for 20 oscillations. Okay. So, let us say again, so we need to set up the vibration, free vibrations in this system, and then for the free vibrations, for the ongoing vibrations, we need to take for 20 oscillations how much is the time. Okay. So, give some initial displacement again. So, it is 15.75 seconds. Okay. So, for 20 oscillations, now the reading is almost 15 point, take as 16 seconds. Okay. So, so once we obtain these readings of the time taken for 20 oscillations and also the data about this calculating the static deflection. Okay. So, we need to have the tabular form, corresponding tabular form for this experimental demonstration, and also some calculation part is remaining. So, we will see the tabular form and how to tabulate the readings and how to tabulate the corresponding how to give the corresponding calculations for this experimental demonstration. Okay. So, in the next session we will see those things. Okay. So, thank you very much all of you. Okay, good afternoon to all of you. So, after the experimental demonstration, it is very important for us to tabulate the readings of the experimental demonstration of finding the natural frequency of free vibrations, okay, of the spring mass system. So, it is very essential for us to note the experimental readings, okay, which we conducted earlier in the session, okay, which we demonstrated earlier in the experimental session which we demonstrated. So, the mass, okay, so that is in 0.338 kgs, okay, so kg is the unit, and L1, so that is the unstretched length, okay, so before the mass is attached to the spring. So, that is in meters, L1 in meters, so that is 0.075. Okay. So, once we tabulate all these readings, so we can do the calculation part, okay, so that you can understand how to do the calculation part and what are the formulae that is those are required for doing the necessary calculation part, and how we compare between the experimental and theoretical natural frequencies. Okay. And L2 is the stretched length for the first reading. So, stretched length is like that is 0.156 meters, and coming to the delta L. So, that is the static deflection. So, you can call this as static deflection. So, this is L2 minus L1. So, that is in meters. Okay. This quantity is in meters. So, L2 minus L1 is 15.6, that is 0.156 minus 0.075. So, it is 1 here and 8. Okay. And so it is 0.156 0.081, okay. So 0.081 meters, okay. And also number of oscillations we have to note down. So this number of oscillations, for 20 oscillations, the time taken for the first reading for the corresponding mass, that is 0.338 kilograms, is the time taken is 14 seconds, okay. So this in seconds, take this as seconds. And the next reading, that is the second reading, okay. So the mass is now varied to 0.438 kilograms, and L1 is the same, that is the unstretched spring length, okay. And after attaching the mass, okay, so this is 0.193, okay. And if you calculate this L2 minus L1, okay, so that is 8, and this is 1, and this is 1, that is 0.118 meters, okay. Meters. And if you can calculate this, okay, again for 20 oscillations, okay, the time taken for the 20 oscillations when the mass attached is to the spring, that is 0.438 kilograms mass for that corresponding mass, okay, for 20 oscillations. So we got this 16 seconds as the time taken, okay. So these are the readings, okay, we obtained from the experimental demonstration of this finding the natural frequency of free vibrations of the spring mass system, okay. So now from these readings, okay, so we need to calculate the theoretical natural frequency. So this is theoretical natural frequency, and this one is the actual natural frequency. So that is the experimental natural frequency. You can call this as experimental natural frequency, and this one is the theoretical natural frequency. So once you calculate this okay, quantities, so then we will be able to appreciate the fact that there is a correlation between the theoretical and actual natural frequency, okay. So that is very much important for us, okay. So we will see the calculation part, okay, in the next session, okay. And so then we will be able to compare the frequency values theoretically and experimentally, okay, from the readings what we have tabulated in this tabular form, okay. Okay, thank you very much. So according to the tabular form noted here, okay, so the calculation part, the corresponding calculation part is important for us, okay. So calculation part, regarding the calculation part, so now for first reading, okay, so let us calculate the theoretical frequency, okay. So theoretical frequency, so that is equal to 1 by 2 pi multiplied by root over g by delta L, okay. So let us substitute the values, okay. So for serial number 1 reading, okay, so g value is the acceleration due to gravity, that is 9.81 root over 9.81 by delta L. So how much is delta L? So delta L is 0.081, okay. So let us calculate this value. Okay, so welcome to the session again. So we are involved in the calculation part of this experimental calculation of this natural frequency of free vibrations of the spring mass system. Okay. So for first reading we have noted these values of this mass and L1 and L2 and delta L, okay, and the capital N and T values. Okay. So now for first reading, so first for serial number 1 reading, okay, so we have to calculate the theoretical natural frequency. So the formula is 1 by 2 pi root over G by delta L, okay, and this 1 by 2 pi, so we have substituted in the place of G 9.81 meter per second square, and this one delta L is 0.081, okay, meters, okay, that is the static deflection. So now, so we can have the value after calculation of this natural frequency by this formula, so that we are obtaining this value as 1.75 hertz. Okay. So the theoretical natural frequency we have obtained as in hertz, okay, that is cycles per second. So that is 1.75 for the first serial number 1 set of readings, okay. And also, so we have to calculate the actual natural frequency. So how to calculate the actual natural frequency is that you divide the number of oscillations, okay. So you divide this number of oscillations with the time taken for the number of oscillations of the number of free oscillations or number of free vibration oscillations. So here you can take as 20 by 14, and the calculated value you can get by calculation part. So we can get as 1.42 hertz, or that is cycles per second, 1.42 cycles per second. So here also you will obtain this in hertz. So this value is 1.42 hertz, okay. So having calculated for the first reading, okay, so that is serial number 1 readings, okay, the theoretical natural frequency and the actual natural frequency, you compare these two frequencies. If we compare these two frequencies, there is somewhat difference, that is 0.3 hertz, almost like 0.33 hertz or 0.3 hertz difference is there between the theoretical and actual natural frequency. So here by experimental means we calculated this natural frequency by experimental demonstration. So we find this actual natural frequency is less than the theoretical natural frequency. So this type of readings we will obtain, okay, once we calculate with the formula, the corresponding formula, okay. So now so let us continue this type of calculation for the second reading also, for the serial number 2 readings, okay. So here the static deflection for the second serial, that is serial number 2 readings, is 0.118 here. So and we will obtain after the calculation, okay, by the corresponding formula, we will obtain the theoretical natural frequency as 1.45 hertz, okay. So 1.45, okay, I am writing here 1.45, okay, after calculation of this theoretical natural. So now we can calculate the actual natural frequency for the second set of readings, okay. So how can we calculate? So by dividing this number of oscillations by the time taken for the number of oscillations. So that is 20 by 16. So here you will get, okay, after calculation of this one, you will get as 1.25 hertz, okay. So this is the actual natural frequency you will obtain for the second set of values, okay, that is 1.25 hertz. Okay. So, having calculated these values of actual natural frequency and theoretical natural frequency, we find that the actual natural frequency values are less compared to the theoretical natural frequency values, and by this, okay, we can say that our experiment was conducted earlier, so that experiment has gone in the right direction. Okay. So, and also one more validation we need to do, so that is calculate the theoretical natural frequency. Okay. So it means theoretical natural frequency by calculating the stiffness of the spring. Okay. So, how to calculate the theoretical natural frequency? By means of the stiffness of the spring. Okay. So, that is also important for us. So, let us proceed in that direction also, okay, so that we can validate our experiment, okay, accurately. Okay. So, here is the, so let us again just go through the calculating the stiffness. So, calculation part, okay, so just, or we can say this is validation of the tabulated results. Okay. So, tabulated results. So, stiffness, so that means for serial number 1 readings. So, we need to calculate the stiffness of the spring. Okay. So, stiffness of the spring, so that is K, capital K is equal to capital W by delta, or you can say this as delta L. Okay. So, that means load by static deflection. So, this load is for the first reading. So, what is the mass we have taken? So, that mass multiplied by the acceleration due to gravity, okay, by delta L, that is 0.081. So, this is the value of the stiffness. Okay. So, this stiffness, because this is load per unit deflection, so this value, that is 40.94 Newton per meter, is the value we will obtain for the stiffness, that is 40.94 Newton per meter. So, that is because stiffness is the load per unit deflection. So, that is why these units will be there, Newton per meter. Okay. And one more aspect. So, after calculating the stiffness, okay, so from the stiffness we can again calculate the natural frequency by means of this formula. So, theoretical natural frequency, okay, so theoretical natural frequency or I can write here theoretical natural frequency. Okay. So, this theoretical natural frequency you can say 1 by 2 pi. So, the formula is 1 by 2 pi multiplied by root over k by m. Okay. So, 1 by 2 pi root over k is the stiffness. So, that is 40.94 by 0.338. Okay. So, here now we are getting this theoretical frequency if we are calculating by this formula, that is 1 by 2 pi root over k by m. So, that frequency we are obtaining as 1.75 hertz. Okay. So, this is exactly correlating with this, okay, frequency, theoretical natural frequency we calculated earlier. So, how did we calculate for this one? So, we have used this formula, that is 1 by 2 pi root over G by delta L. Okay. So, by that we calculated this theoretical natural frequency, and this is correlating well with this, with the value obtained by this formula for theoretical natural frequency. Okay. So, this is for first reading. So, we can again demonstrate this same calculation part, okay, for the next set of readings, that is serial 2 readings. Okay. So, if we see here, so here this W will be, so because this mass will be changed for the next set of readings, that is 0.438 multiplied by 9.81 meter per second square by 0 point, so 0 point here, so it is 0.118. So, the corresponding stiffness for the second set of values, okay, corresponding stiffness of the spring for the second set of values is that is 36.41 Newton per meter. Okay. And the theoretical natural frequency again we can calculate for the corresponding stiffness and the corresponding mass here. So, this is this will be 36.41, okay, by 0.438. So, you will get exactly, okay, the same value you have obtained earlier, okay, by the calculation, that is 1.45 H. Okay. So, by this calculation part, by demonstrating with the experimental things, okay, and by these theoretical values, okay. So, we have done this experiment, that is to find the natural frequency of free vibrations of the spring mass system, and so we can, it is evident from our calculation part as well as the experimental demonstration. So, that we have calculated the theoretical natural frequency, that is theoretical and experimental natural frequency of free vibrations, and you can see there is some difference between this theoretical and experimental natural frequency, and also by two ways we calculated this theoretical natural frequency. So, one by the static deflection and the other by calculating the stiffness of the spring. Okay. So, we calculated this part. So, here the stiffness is varying, okay, according to the mass. So, that is attached to this to the spring. Okay. So, by this we can write the result of the experiment. Okay. So, the result of the experiment results. Okay. So, we can write the results obtained for this experiment. So, the theoretical natural frequency of the spring mass system of stiffness 40.94 Newton per meter is 1.1 1.25, sorry, it is 1.75 heads. Okay, it is 1.75 heads. Okay, and also you can write the experimental natural frequency, the actual natural frequency, of the so here I forgot to write of the free vibrations of the spring mass system. Okay, so the actual natural frequency of free vibrations of the spring mass system of stiffness 40.94 Newton per meter is. So the actual natural frequency, that is 1.42 hertz. Okay. So for the corresponding stiffness value, so the corresponding stiffness value also we can note down here. So this is Newton per meter. So that is okay, 40.94 Newton per meter. So these are the theoretical and experimental, the actual natural frequency values, and want to obtain for already we have obtained for the second set of readings also the stiffness, that is 36.41 Newton per meter. Okay. So now we can write. So these are the results we obtained for the first set of readings. So with the stiffness value, that is 40.94, okay, of stiffness. So we have obtained the theoretical natural frequency 1.75, and the actual natural frequency for the corresponding stiffness of 40.94 Newton per meter is 1.42 hertz. Okay. So so the same type of results can also be written for stiffness, okay, that is 36.41. Okay. So for this 36.41 Newton per meter stiffness is the 1.45 hertz. Okay. And the actual natural frequency of free vibrations of the spring mass system of stiffness 36.41 Newton meter is 1.25. Yeah, actual natural frequency is 1.25 hertz. Okay. So this concludes the experimental demonstration and the calculation part of this experiment of finding the natural frequency of free vibrations of the spring mass system. Okay. Thank you very much.